Okay, Steve, are you ready?
No.
Oh. Okay, then let me announce the final speaker of today, Steve Awodey, and he will speak about.
Well, I'm not ready yet. I'm trying to share my screen. I wanted to practice before, but I wasn't able to. So let's try again. I think this is what I want. How's that look?
Yeah.
Great. Okay, now you can introduce me. Thank you for waiting. Get rid of that.
Okay, so our final speaker of today is Steve Awodey from Carnegie Mellon, and he will speak about univalence in infinity-topoi.
Right. Okay, how does that look? Do I have a proper screen sharing there?
It is okay.
Okay, good. Thanks. So yeah, the topic is univalence in infinity-topoi. Wait a minute. I have a Zoom thing visible on my screen. Is it visible on yours as well, or is that just me? I guess I'm okay. I can't hear you. So. Okay, I'll just carry on.
Yes, yes.
Yes, it's okay, or yes, you have the Zoom thing visible.
I think it's okay.
Okay, thanks. So, well, the notion of an infinity topos has been around for some time, and lately there has been some movement toward trying to find a notion of an elementary infinity topos, maybe by analogy to the notion of an elementary one topos. At the last CT in Edinburgh, there was a talk by Nima Razek, who in the meantime has a paper on elementary infinity topos. And Mike Schulman has written on this topic, and there are other proposals around. So this is kind of what I'm looking at, as well as I'm pursuing this idea of an elementary infinity topos and what should such a thing be. So the idea, of course, is that we're proceeding by an analogy to the notion of an elementary topos and its relation to a Grothendieck topos. I'm going to gesture with my cursor here. Can you see that? Yes? I need somebody to,
yes,
I can't see you, so I need you to answer me. Okay, thanks. Okay, so an elementary topos is, of course, a generalization of a Grothendieck one topos in a certain direction, right? It captures some aspects of the notion of a one topos, but it omits some others. For example, it omits the co-completeness and the small generation. So when we try to find the notion of an elementary infinity topos by analogy, we don't really know what to preserve and what to omit. So one way to help ourselves there is to look at a different analogy, that is the analogy with the relationship between some logical systems. So an elementary one topos, of course, also describes a notion of logic, namely intuitionistic higher order logic, or as it was called earlier, I-hole. And so we might try to use homotopy type theory there as an analogous logical description of the notion of an elementary infinity topos. And indeed, this relationship between these three different things, the semantic side, if you will, and the syntactical side, and then the abstract algebraic approximation there in the middle, is something that occurs also in another setting, which we can maybe learn from. And that's this one, where we have here the notion of a Heyting algebra as an algebraic abstraction of a topological space, where by space here, I just mean a locale or a frame of open sets of a space. And that's guided also by the logical description in terms of intuitionistic propositional logic. So whatever the relationship is between these three things, it seems to obtain here between these three things, and that's what we want to do here between these three things. Now, this one topos that we're describing here in three different ways is repeated down here as a kind of, maybe it's a zero topos, right? This is a topos down here where the Hom sets are -1 types, and then this is Hom sets are 0 types. And if you're an old-fashioned one topos theorist like me, when you start looking at infinity toposes, you have the feeling that you've spent your whole life living in the basement and the ground floor of a building that turns out to be an infinitely tall skyscraper. You just didn't know you were there. So we're going to look at this situation a little bit more closely in order to figure out what to do up here in this situation. So what's happening here is we have certain infinitary operations or some infinitary character here, and we capture it using some finitary algebraic descriptions. So for example, the infinite distributivity law in a frame is replaced by the finitary exponential here, the implication, the right adjoint to conjunction, and having that implication makes the conjunction be a left adjoint and therefore commute with arbitrary joins. And similarly, the exactness in a one topos, which doesn't figure at all in the definition of an elementary one topos, arises from the sorry. Okay, the exactness in an elementary, in a one topos, a Grothendieck one topos, arises in the elementary case, not by putting it in, but by some algebraic operations that we've picked out, namely having these power sets and subobject classification. It makes the notion of a one topos algebraic in a strict sense. It's monadic over cat or over graphs, and it's monadic over itself by the power set functor or power object functor. And so the limits and co-limits interact in a very nice way. And so that's the sort of thing that we're hoping to arrive at up here in the infinity case. But here again, maybe there's a kind of underdetermination. Why did we choose these particular constructions to go into our elementary notion? They work well to capture some of the infinitary character here, but they're not entirely determined. I think that really they're determined by considering also the logical interpretation. So we have, let's look at this one-dimensional case here. We have an interpretation of I hole into the semantic objects, the Grothendieck one toposes. And what we want to do is we want to maybe axiomatize the image of that interpretation in a one category so that the interpretation can actually happen here in the notion of an elementary one topos. And moreover, the notion of an elementary one topos should be sufficiently rich to capture all of the logical structure. So this little wiggle here suggests that this is somehow an algebraization of this syntactical finitary notion. More precisely, it gives us sufficiently many semantic structures to prove the completeness of this logical system. And here too, intuitionistic propositional logic is complete with respect to algebraic semantics in hiding algebras. And intuitionistic higher order logic is deductively complete with respect to just the semantics in elementary one toposes. And this is in both cases because we have syntactic models. And that kind of gives us a guide maybe to what structures we might choose here to put into our elementary axiomatization. If we had taken something different here, like dependent type theory, then we would still have the interpretation into Grothendieck one toposes, but here we would end up with a different notion. We would end up with something like locally Cartesian closed categories And here we would have sigmas and pi's. So I want to say this notion of an elementary one topos, maybe in summary, it has a conventional aspect as well, a practical aspect that we've chosen. It's not a distinguished, there's no distinguished choice for what to put there. It's partially determined by what we're doing over here. And now we can use that insight to continue, because we do have an interpretation of homotopy type theory into Grothendieck infinity toposes, which was given to us recently by Mike Schulman. We, geez, I'm sorry I didn't turn off my stuff there. I hope you're not seeing those. Mike Schulman has, I mean, we've known that HoTT interprets into infinity toposes in a general way for about 10 years, but Mike has recently shown that indeed every Grothendieck infinity topos admits an interpretation of homotopy type theory. So we can use that in the same way to guide our choice of the notion of elementary infinity topos. So in particular, we want to have syntactic models of elementary infinity toposes, or syntactic elementary infinity toposes coming out of the type theory. And so in particular, we're going to put in these path objects, and that will kind of allow us to do some homotopy theory, having path spaces like this. And it allows us to formulate the notion of a homotopy limit and homotopy co-limit. And then maybe the newer idea, and the one that I want to tell you more about today, is this idea of putting in a univalent universe. And that's our finitary way of capturing the infinitary notion of descent, which is one of the defining properties of an infinity topos. The one definition or characterization of infinity toposes is due to Charles Resk, and one of his axioms, that's in terms of model categories, Quillen model categories, and one of the axioms is the descent condition. So I'll explain that a little bit more later on, and I want to describe now in the rest of the talk the connection between descent and univalence. So here's a little bit of background. We have this kind of interpretation of this logical stuff into the semantical infinity topos. The dependent type theory, the sigmas and pi's form a locally Cartesian closed infinity category. The type of propositions is the subobject classifier. These Martin-Löf universes correspond to what's called an object classifier, or a system of object classifiers. I'll explain that in a minute, in infinity topos. And then the homotopy theory, which comes from the identity types in intentional Martin-Löf type theory, is described over on this side, maybe in terms of a Quillen model structure, which is the basic ingredient for, or at least one way of describing an infinity topos. So up to the blue line, most of this I told you last time I was here in Genoa in 2010 at the CT. So that's our background. We all know that from the last CT. And now what I want to tell you about is this new idea of relating the crucial univalence axiom due to Vygotsky, which is one of the basic fundamental extensions of Martin-Löf type theory, which constitute homotopy type theory, this univalence axiom, and how that's related to the descent condition of an infinity topos, which can be written in this way as a kind of homotopy equivalence there, which commutes co-limits with limits. So we'll talk about that a little bit more in a minute. Let's start by looking at the one topos case of a subobject classifier. Of course, the subobject classifier we know is a representing object for the subobject functor, the contravariant presheaf of equivalence classes of monos with pullbacks. So that's a contravariant functor. It's represented by the subobject classifier. Because it's a representable functor, it's continuous. And so it takes colimits to limits, right? So that's a familiar property of the subobject, the presheaf of subobjects. Here's a particular instance just to remind you of what this means. Let's suppose, so we have this descent property for subobjects. Let's suppose we have an epimorphism here and consider its kernel pair. And we have a subobject, and we want to know, does this subobject come from one down here by pullback along the epi? Well, you can test for that by pulling it back twice along the two legs of the kernel pair. And if, when you do that, you get the same subobject both times, then indeed it comes from a unique subobject down here. That's a familiar logical statement. It just says that if you have a predicate and it respects an equivalence relation, then it's really a property of equivalence classes. So in this case, in the topos case, it's this descent property which arises from the representability of the subobject classifier. So let's look at a similar case over here. In the case of an infinity topos, we have what's called an object classifier. It's kind of like a subobject classifier. It classifies small maps. So let's suppose we have a notion of small map. I'll remind you in a minute what that is. Then there's a classifying map into this small map classifier, which presents our small map here as a pullback of a universal one. But it's a weakly universal in the sense that this classifying map is not unique the way it is for a subobject classifier. And because of that failure of uniqueness, we don't have this representability condition that we had for subobject classification. Now, that's not only because this thing is too big to be representable. Even if we restrict to small maps, we still won't have an isomorphism like this with this set and this category. We won't have uniqueness in the condition there of classification. However, we do have something else, and that's what I want to tell you about now. So let's have a look. These object classifiers we can build in the following way. Let's look at presheaves to keep things simple. So in sets, first of all, I should write set over here. We have these subcategories. And what I'm doing here is I'm saying, okay, take some cardinal and take the subcategory of all sets of strictly smaller size. So here, for example, is the subcategory of all finite sets. And here's the subcategory of either the empty set or one element sets. And here's the subcategory of all sets of size strictly less than some cardinal number kappa. And now, given these subcategories in the presheaves, we can make these universes. These are usually called Hofmann-Streicher universes in the type theoretic literature. And the way this works is this: Vk, for some k, is a presheaf, and it's defined at an object C by saying, take the set of all small valued functors on, or presheaves on the slice category of C over C. So this is a Hom set in cat, right? This is the category of kappa small sets. And this is the set of kappa small valued presheaves on the slice over C. Now this thing is covariant in C, and therefore this thing is contravariant strictly in C, and so this is a presheaf. And that presheaf, Vk, well, it kind of lines up with these other Ks, and it has this classifying property. Well, if you were already familiar with the case of 2, V2 is none other than the subobject classifier that we already know. And then the other ones are generalizations of that subobject classifier, and they classify small maps which are small in the sense that the fibers of this map over any representable all have size strictly less than, I should have written strictly less than K or kappa. Okay, so these are small maps of size kappa, and this guy classifies maps, such small maps, by pullbacks. And this alpha here, the classifying map, is blue to remind me to now mention the fact that this is not unique, again, but it is unique in a certain way that we can explain like this. If we look at this object classifier, VK, it determines an internal category, which I'll write there as bold VK, by the familiar construction of the full internal subcategory of a map. And that internal category, in fact, represents, now by homing in, a pre-sheaf of categories, and that pre-sheaf of categories is equivalent to these slices, the slices of pre-sheaves over X, where I restrict to small maps of size K. So in that sense, this slice category operation is representable. It's representable by these internal categories. And so these classifying maps, this is another way of saying these classifying maps are indeed unique, but they're only unique up to natural isomorphism, where this is, of course, not a category. So natural isomorphism means with respect to this category, homing into this category, or this with respect to these category pre-sheaves there of categories on C. So that's the sense in which these object classifiers classify families. And as a corollary, just like for the subobject classifier, it turns out that this pre-sheaf is again representable and therefore continuous. Just as for the subobject classifier and the pre-sheaf of subobjects, we now have a continuity condition which says, if you look at the slice over a limit, or sorry, a co-limit, then that's a limit of these slice categories. So this is one description of being a stack. So it's saying that this pseudo-functor of small families is in fact a stack over the category E. It's something that I learned a long time ago as a graduate student from a paper by Marta Bunga and Bob Perret, both of whom I think are here in Genoa. Okay, so here we have this internal poset in pre-sheaves now. I'm talking about pre-sheaves. We have this internal category. Each of these things are representing some functors. This one is representing up to isomorphism, the subobjects. This one is representing up to equivalence of categories, this self-indexing of the topos over itself. And I would like to generalize this now to higher categories and their appropriate notions of equivalence. And I'll just cut right to the chase in view of the time. And the punchline is that one way of giving this generalization is as follows. Here we go. It arises from the univalence axiom. So first of all, informally, in HoTT, we have a universe, which is a kind of object classifier, and we say that it's univalent if it has this property. When I look at the maps that are classified, so here, for example, this family A is classified by alpha, then if these classified maps are equivalent over X, then their classifying maps are homotopic. So there's a correspondence here between equivalence classes, if you like, or homotopy types over X and homotopy classes of the corresponding classifying maps. So that's what I'm saying, where the homotopy here is paths in the universe. right? This is families, X index families of paths in the universe between the classifying maps. And equivalence here is fiber-wise, because we think of dependent types as fibrations, fiber-wise equivalence, and therefore it's a family of homotopy types. Okay, more formally, we can make this precise in HoTT by saying these equivalences are actually parametrized by a classifying type over the universe. You construct that in the type theory. And there's a factorization of the path space of the universe through this classifying type for equivalences. And then this correspondence between these two things arises as follows. If I have a homotopy between the classifying maps, then that gives rise to a factorization of X of the pair alpha beta through the path space. And then that factorization further factors through the classifying type of equivalences, and that gives me this equivalence between the families classified by alpha and beta. And now the more precise statement then of this correspondence is this, that these two types, which are just the pullbacks of these two things along the pair alpha beta, are themselves in turn equivalent. And that's exactly the kind of homotopy type theory formulation of the univalence axiom. It says that homotopies between maps into U are equivalent to equivalences between the things classified by the maps into U. And that notion, the univalence notion, can be formulated also in an infinity topos as described by a Quillen model category. So I'll do this very quickly because I guess I'm running out of time here. Let's suppose we have a Szyszynski model structure on a presheaf category. That is to say, the monos are the cofibrations. If we have an object classifier, like the thing we saw a moment ago in presheaves, we say that that's univalent if this corresponding map, which is just the transport along the paths, is a weak equivalence in the model structure. So this transport works like this. Whenever I have a path in the universe between two points, alpha and beta, then that path induces, by transport, a map between the objects classified, and that transport map, this should be a star here, that transport map is itself a weak equivalence in the sense of the model structure. So there, in model theoretic terms, we have a formulation of the univalence axiom, and it passes to the presented infinity topos in this way. It says that when you have a univalent universe there in your infinity topos, then there is an equivalence of infinity categories between this slice category, and now, because we're in an infinity category, this Hom set is a Hom category, but it's also an infinity category. And we have an equivalence here of infinity categories between these things. And therefore, this slice operation is continuous because it's representable. And so we get this descent condition, which is familiar from the axioms for an infinity topos. So just to give a quick picture of descent, let's suppose we have a push out here, a homotopy co-limit on the bottom of my cube, and then I have pullbacks here on the sides. Then what the descent condition is telling me is that in that case, there must be a unique up to homotopy guy down here, which pulls back like this to make the cube here all pullbacks on the sides. And again, here, of course, a push out on the top. So that's the usual or familiar formulation of descent for an infinity topos. And it, of course, follows here from the representability of this operation. And that follows from the univalence of the universe. So that's what I wanted to tell you, the connection between univalence in homotopy type theory and descent in the notion of infinity topos. The proofs of this in terms of Quillen model categories go back to, the first one is by Voivodsky for the special case of simplicial sets and the Kahn-Quillen model structure. It's about 10 years ago. Schulman gave the first proof in greater generality. I don't know what happened there. The first proof in greater generality for, I guess this is a directed category here, C, for simplicial presheaves and a Reedy model structure. More recently, Chirika Kohn and Christian Zuttler gave a proof for a special case of cubical sets. These are specific cubes with some very specific algebraic structure, and using methods inspired by type theory. And then since then, I've analyzed and generalized this proof to a variety of different cases involving presheaves and simplicial presheaves, using a model structure that's inspired by this type theoretic one, which I, for lack of a better name, call the tiny interval model structure, because it makes use of the assumption that you have an interval, like in a Szynski model structure, but we require the interval to be tiny in the sense of Leverrier. And examples of this include also cases of realizability and various different cubical sets, including some symmetric cubical sets. So those will also be interesting examples of infinity toposes. Thanks very much. That's the end of the talk. I think I stop sharing and then I can go back to this. Great.
Are there some questions? Yes.
Do we have a question?
I have one comment. I would like to know your opinion. So for me, elementary topoi stem out from Leverrier's attempt to do ETCS, which was an old project, which was to axiomatize in a finitary way let's say the category of sets, let's put it this way. So it was looking at the category of sets and he said, okay, I like this and this axiom. I think it's kind of important for me, so let's axiomatize it, right? And this is how elementary topoi were born. I mean, this is not historically, I'm making a mistake, but I think you get what I mean. So for me, in an elementary infinity topos should be something similar. We should look at the category of spaces and say, okay, what do I like of this category? What is fundamental of this category? And I write down what I think is important, and this should be the notion of elementary topoi and infinity topoi. And instead, recently, people have been working by analogy with the one topos case, which in my opinion is a little bit strange. Now, today, in my opinion, you go more in the first direction I was discussing, but still not precisely in that direction. So I wanted to know, what do you think? You think I'm wrong? You think, who's right in this?
Yeah, great. Okay, thanks. That's a great question. So I have two things to say about it. The second thing is that you're wrong, but the first thing is, it's a great example of what I just said, that the notion of an elementary, whatever, infinity topos, elementary topos, is partly a practical matter. It has to do with which aspects of the concept you want to emphasize or capture, right? There's no kind of distinguished way of doing it, because if what you want to capture is the elementary theory of the category of sets, then you'll have a different choice for your notion of an elementary topos. And that's where I think you're a little bit wrong there, if I may say so bluntly, because if that's all we were doing, you would put in well-pointedness in your elementary axioms, which we don't do for a elementary topos, but which we did for the elementary theory of the category of sets. And it follows then that it's Boolean and that it's the subobject classifier is in fact two-valued and so on. So none of that stuff goes in there in the definition of an elementary topos. And similarly, for an elementary infinity topos, if all we wanted to do was capture the category of spaces, we would do the same thing. For example, we would make it two-valued. It has a subobject classifier, but the subobject classifier is two. And the subobjects are just Boolean. The category of spaces as an infinity topos is Boolean and two-valued. So we don't put all those additional conditions in there because we want to generalize, at least I don't, you might, because it is, a matter of taste. And what I'm looking for is something that corresponds not just to the category of spaces or infinity groupoids, but more generally to a category of sheaves of infinity groupoids or an infinity topos, not just the one that is spaces. And then I don't choose to put in those additional conditions like Booleanness. Does that answer your question?
I have to say it doesn't, because I didn't mean I wanted to portray the category of sets. Of course, I didn't want to say I want a full axiomatization such that a category that satisfies the axiom is the category of sets. In fact,
no, that's not what I'm saying. That's
not every. Sorry?
That's not, I didn't say you're trying to capture exactly the category of sets. It's a question of which aspects do you want to put in your elementary notion. And if all you want is sets, then you would probably choose to put in Booleanness or well-pointedness or something. I think it's a practical question. What do you want? What do you choose to axiomatize in the elementary notion? I don't think it's distinguished by anything.
No, I agree with this, but maybe.
This is partly an argument against Mathieu Anel, who doesn't put universe, or at least I missed his talk. It was too early in the morning for me, into the elementary infinity topos. He gave a nice example of the, truncated coherent spaces as an elementary infinity topos, which doesn't have a universe. And although maybe he's backed off on calling it an elementary infinity topos now, but it's a great kind of test case. Do we call that? It has descent. It's locally Cartesian closed. It's like the category of finite sets, which is an elementary one topos. The only thing it's missing is the universe. It has univalent maps, but not a univalent universe. So where do we draw the line? What do we call an elementary infinity topos? And I'm arguing that I think it should have a universe in it based on wanting to also interpret HoTT, which gives a kind of algebraic or finitary way of capturing the descent condition by putting in a univalent universe. It's a practical argument.
Okay, I think we have to close the discussion here.
Oh, sorry. I went on too long.
We're a little bit over time, but since this is the last talk of today.
Yeah. I'm glad to hear any further comments or questions people have by email. You know my email address.
Okay, so let's thank the speaker again and all the speakers of today.